The gravitational field. Well, gravity caused by the Earth we can calculate in two ways. We can calculate the gravity is m times g, the gravitational field constant we already learned in the beginning of learning physics, which makes our calculation rather easy. 100 kilograms times 9.81 newtons per kilogram is 981 newtons. We can do it with the formula of Newton's law of universal gravitation, and which gives us here the constant 6.67 times 10 to the power minus 11, the mass of the Earth 5.98 times 10 to the power 24 times 100, if we take the same mass of course, divided by the square of the radius 6,378 times 10 to the power 3 or 10 cube in that square is 981 newtons the same. Those are equal. So, which means we can see these two formulas as equal, and so we have a formula in fact to calculate our gravitational field, which is the universal gravity constant times the mass of the object creating the field divided by the radius squared. And also we notice now that the units of our gravitational field, the SI unit, newtons per kilogram, is in fact the same as the SI unit of acceleration, which is m divided by second squared. Newton is in fact m, the force, net force is m times a, which force is in newton, mass is in kilogram, and acceleration is in meter per second squared. So we can replace the newton by this. We eliminate the kilograms and we are left with our acceleration, which proves that this is equal to this. Example, calculate the gravitational field on Mars. Mars's density of 3,933.5 kilograms per cubic meter and an average radius of 3,386 kilometers. Here's our formula. But of course we don't have the mass of Mars, so we need to use another formula, which is the density is the mass divided by the volume. The mass is the density times the volume, so which makes the mass is the density times the volume of a sphere, 4 divided by 3 pi times r to the r cubed. G is universal gravity constant times our mass, which we have here, divided by r squared. Of course, we have r cubed here and r squared here, which leaves us with r here. And if we fill everything in, a universal gravity constant, the density of Mars, and here we fill in the radius of Mars, we get 3.72 newtons per kilogram. Now, factors influencing the gravitational field. We work with the gravitational constant as 9.8 or 9.81, depending on where we are, but this is different for every place on the planet. For example, if you're on a higher place, height is different at different places, or you can be in an airplane. In both cases, r is greater. You are further away from the center, so your g, gravitational field constant, will be smaller. Another factor influencing the gravitational field is density. The density differs on different positions on Earth. We have here our formula for the gravitational field. Well, we can replace the mass by the density times the volume. Well, the density differs on different positions, so small variations, whether you are on a dense rock or a lighter medium, can give different gravitational field constants. The final factor influencing the gravitational field is the latitude. First, flattening. The Earth is not a complete perfect sphere. There is flattening, which causes different distances to the center. This distance is smaller than this distance. From the North Pole, you're closer to the center than from the equator, which gives a different r, so gives us a different gravitational field. And then we have the angular velocity. The angular velocity is different on the North Pole and on the equator. On the North Pole there is no angular velocity, or at least you're not really describing an orbit or a circular path, no movement at the North Pole, so net force is 0. The normal force equals the gravitational force, which makes the formula for our North Pole: the normal force we experience is the gravitational force is m times g for the North Pole. But at the equator we have a resulting movement because we have a centripetal force. Centripetal force m times a, which makes that the normal force, which pushes us upwards at the equator, equals the gravitational force minus the centripetal force. Centripetal force formula m times r times omega squared, which makes that the gravitational force pulling us towards the center, if of course the Earth would be perfectly sphere, is m times g North Pole minus this one, m r times omega squared, which makes that what we feel when we are at the equator, we don't think when we are at the equator that we're constantly orbiting or constantly rotating the center of the Earth. We just feel Fn, the force which pushes us upwards, is m times g equator. The field we experience at the equator is m times g of the North Pole, the field we experience at the North Pole, minus the force we need to be on the circular path, which makes that g of the equator is g of the North Pole minus the radius of the Earth times the angular velocity squared.